In this lesson, we are going to learn about something called redox reactions. Redox is actually an abbreviation, a mashup, if you will, of two words. These are reactions that are driven by the loss of electrons. Loss of electrons is known as oxidation, and the gain of electrons. The gain of electrons is called reduction. So redox is a blend of the word reduction and oxidation. You can't have a loss of electrons unless there's some other chemical species that wants to gain them. You can't have oxidation without reduction. You can't have reduction without oxidation. We're going to learn how to represent a redox reaction by understanding both halves of this total reaction. So if we take a look at this Bohr model, we see 12 protons, 12 neutrons, and we see a total of 12 electrons. So this is starting out as magnesium, the atom. It's neutral with 12 protons and 12 electrons. Down here we have an element with 16 protons, 16 electrons, so it's neutral, but with 16 protons, this is sulfur. But you can see here that the magnesium has 2 valence electrons, whereas the sulfur is missing 2 electrons. It's got 6 valence electrons, so it wants 2 more. So what will happen is that this electron, this magnesium, will lose 1 electron, and then the magnesium will lose a second electron. Okay, so magnesium loses the electrons, and we show that in a chemical reaction by showing an arrow turning that magnesium has turned into magnesium plus 2, right? Because now it has, it still has 12 protons, but now it's only got 10 electrons. So it went from 0 charge to a plus 2 charge, and it did so by giving off 2 electrons. Meanwhile, those 2 electrons were received by this sulfur. So this sulfur neutral atom gained those 2 electrons, right? Those are those 2 electrons right there. It gained those 2 electrons, and when it did, now with those extra 2 electrons, it now has 18 electrons, giving it an S-2 charge. So magnesium 0 lost 2 electrons, sulfur 0 gained those 2 electrons. Okay, so putting it together, these are 2 halves of one reaction. What we had to start with was magnesium, the neutral atom, and sulfur, the neutral atom. And it turned into Mg plus 2 and S minus 2. Well, that's a cation, that's an anion. Together they're going to attract one another, and they're going to become MgS, right? This one has a plus 2 charge, this one has a minus 2 charge. In the end, those charges cancel, but this is how we draw the net equation for this redox reaction. But this is sort of breaking down where the magnesium lost those 2 electrons and the sulfur gained those 2 electrons. Now, the reactions where this happens, we've already studied these a little bit. Okay, common reactions that are considered redox reactions, where someone is losing electrons and someone is gaining them. And the first type of redox reaction is synthesis, where we have 2 elements, element A, element B, becoming a compound, right? So this is an element, this is an element, so element plus element turns into a compound. Decomposition, you have a compound turning into its component element and its other component element. Okay. These are redox reactions. The third type is what we call single replacement, where we have one element and one compound on each side, the reactant side and the product side. But there's 2 possibilities here. If you have a metal plus a compound, so this metal is an element, but it's a metallic element. So let's say that's what A is, right? Here's your metal. Here's your compound. And because this is an ionic, it's got to be an ionic compound, this metal will replace this metal B in this compound. So A and B will switch places. That means B will end up being a metal that has been replaced or displaced. And then A takes the place of where B is. So we have a metal element reacting with a compound, turning into a different compound plus a different metal. This is a common reaction. This is what happens in batteries. This is what happens when we dig up rock from the ground that contains metal, and this metal in the ground is in its combined state. But if you want that metal to be in its metallic state, you have to do this kind of reaction, a single replacement reaction, to free up that bound metal. But we can also do this with a nonmetal in a compound. So let's say, for example, that A is a nonmetal, and it's going to react with the compound Bc. But because A is a nonmetal, A and C are going to switch places, right? That's going to make C, the nonmetal, exist all by itself, and that A has now taken the place of C, and we have a new compound, Ba. Okay. So single replacement works for metals or nonmetals, although for nonmetals, a nonmetal single replacement is a bit more unlikely, but we will see it in this course. Now, in order to work with these kinds of reactions, what we're going to ask you to do is you will have to, and the end goal here is to ultimately be able to decide what's going to happen when we make these reactions work towards energy production, for example, in a battery. Okay, so ultimately this is what we are working on, but to do that, we are going to have to first identify the charge of each species in a redox reaction. Once we know the charge of each species, we can determine which species is oxidized, which is reduced, and what ions are not participating in the reaction, just existing as a spectator ion. And if I'm only giving you the reactants, or I'm only giving you the products, you have to complete and balance the reaction by predicting the products of whatever is missing. Okay, so that is the other skill that this will help you develop. So let's start with that first one, identifying the charge of each species in a redox reaction. To do that, there's a couple of basic rules. Elements all by themselves, not in a compound, right? So elements by themselves are not in a compound. They will always have a zero charge. They will always be neutral. So for example, if you just see the element symbol aluminum, it's going to have a charge of 0. We're going to put a little 0 above it. Cl2, this is an element. It is a diatomic element, but it is not a compound. So if you see Cl2, you're going to give it a charge of 0. Fe, iron, when you see iron not in a compound, it's going to have a charge of 0. Put a little 0 over it. Basic rule number 2, the charge of the ions in a compound can be looked up on reference table E, if it's a polyatomic ion, or you can look up on the periodic table if it's a regular simple monatomic ion. Okay. Basic rule 2A. If the cation element has more than one charge listed, we're going to use the negative ion's charge to determine the charge of the positive ion. So, for example, okay, we have Al2SO4 3. If we consult our reference table E, perhaps you might already recognize that, right, that this SO4 is something called sulfate, right? If we look at it right there, sulfate, it's a -2. So this polyatomic ion right here is a -2. Now, aluminum, Al2, there's two aluminums, but what we can see when we look up aluminum's charge, a charge on a single aluminum is a +3. Okay, and you can see that those are the charges where we could use those as the drop and swap to get those subscripts down there. But this is the skill. We're kind of reversing the drop and swap to figure out the charges. Okay, let's take a look at Fe3PO42. Fe can either be a +2 or a +3. We have to figure out which one it is. Since it's not obvious, we have to go to reference table E and look up phosphate's charge. Phosphate's charge is a -3. Because there's two of them, that means that this charge on this Fe has to be a +2, basically the reverse of the drop and swap. Okay. All right, let's take a look to see how this looks when we expand it and put it, and we do this within the context of an entire chemical reaction. Okay. Taking a look, we have an equation here. Silver plus oxygen turns into silver oxide. Okay, take a look. This chemical formula right here is just an element. Elements have a charge of 0. O2, that's just an element. It's diatomic, but it is just an element, so it has a charge of 0. The charge of the silver and the charge of the oxygen, if we take a look at the periodic table, the charge of a silver is always +1. The charge of an oxide is always a -2. So we're just going to put those charges above. Okay, that's all we're looking at right now. We'll take it to the next step in just a moment. Let's take a look at this reaction right here. Here we have potassium, not in a compound. It's just K. That's going to have a charge of 0. Al2SO43, if we look up the charge of a sulfate, it is a -2. If we look up the charge of aluminum, it is a +3. On the product side of this reaction, potassium, when it is in a compound, has a charge of +1, and this sulfate has a charge of -2. Over here, we have aluminum all by itself. It is a charge of 0. FeO, right? This is one of those that iron, it could be a +2 or it could be a +3. We have to figure out which one it is. To do that, we have to look at the charge on the anion. We know oxygen has to be a -2 when it is combined in a compound. So because this is a 1-to-1 ratio, we know that this iron is a +2. On the product side, we have iron, the element, it's a charge of 0. We have oxygen, the element, we have a charge of 0. Our last example here, calcium plus hydrochloric acid turns into calcium chloride and hydrogen. Ca, element all by itself, it's a 0. HCl, we have Cl -1, and interestingly enough, H is a +1. I know that there are more than one charge listed here, but because hydrogen is a non-metal, we're always going to take that top one. So that is a +1. Now that's interestingly enough, you might be noticing that that's a covalent compound because it's two non-metals. So you might be wondering why there are charges. This is something that we'll cover in a later topic. For right now, we're going to treat it as if it has apparent charges. Over here, the CaCl2, we know the chloride's a -1. This calcium, we can verify indeed that this calcium is a +2. And lastly, this hydrogen as an element is all by itself, so it has a neutral charge of 0. Okay, so what we have just done, right, we identified the charges of each species. by following these simple basic rules. Once you have identified the charges on all the species, we are going to use that information to help us determine what chemical formula got oxidized, what chemical formula got reduced. So remember, if something is oxidized, that means it has lost electrons. You can remember this as the acronym OIL. Oxidation is the loss of electrons. Now, when you lose negative electrons, so for example, if you remember magnesium, the example we just saw, it started off with 12 protons and 12 electrons, right? And then it went to magnesium +2 because it had 12 protons, but only 10 electrons. Okay, so when an atom loses those 2 electrons, the charge goes from 0 to a +2. So losing electrons, the oxidation number becomes more positive. Now, a species that is reduced is the substance that has gained electrons. You can remember this as rig, oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. Now, when an atom gains electrons, it becomes more negative. Now, sometimes there are ions that are just going along for the ride in a redox reaction. And if you find that an ion has neither gained nor lost electrons, its charge just does not change, we say that that ion is called a spectator ion. Okay, so what we're going to do now is take a look at these reactions that we just wrote oxidation numbers for. And we're going to try to identify what gets oxidized and what gets reduced by noticing which substance had a charge that got more positive and which substance had a charge that got more negative. Now keep in mind, when you are identifying who is oxidized and who is reduced, you are choosing from the reactant side. Okay, so Ag0 or O20, which one of these is getting oxidized? Well, if we look here, this silver starts out as a 0 and it ends up as a +1. So this Ag0, its charge got more positive. It got more positive because it lost electrons. So what substance is the substance that gets reduced? Well, let's take a look. We have oxygen with a 0 charge ending up as a negative charge. So the substance that got reduced is the O2 with a 0 charge. Again, when I ask you who's getting oxidized, who's getting reduced, you are choosing from the reactant side only. Now, there is no spectator ion. There's no ion whose charge did not change, so we're just going to put an X for that one at the moment. Okay. Let's look for a few more examples here. Okay, we've got K0 turning into K +1. So this K0 went from 0 up to a +1, so K0 is what got oxidized. Let's take a look at the aluminum. The aluminum is a +3. It ends up as a 0. So from +3 down to 0, that is what gets reduced. We say Al +3 is the species that gets reduced. Now, if you'll notice, the SO4 -2 stayed as an SO4 -2. So we would say that that sulfate ion is a spectator. Nothing happened to it. Its charge remained the same. Example number 3. We're starting off with iron +2. It is ending up as iron 0. Okay, so in this case, the iron +2, that charge is going from +2 down to 0. So that Fe +2 is what is getting reduced. It's gaining electrons. The O -2 that charge is going up to a charge of 0. So the substance getting oxidized, whose charge is about to become more positive, is O minus 2. There is no spectator, there's no ion whose charge is remaining constant. Okay, let's take a look at example number 4. Let's take a look at calcium. Calcium starts out as a plus 0. It ends up as a plus 2. So Ca0 gets more positive, does so by losing electrons. So we say that Ca0 is what is oxidized. Okay. Here I see H with a plus 1 charge. Hydrogen starts out as a plus 1, but it ends up being H20 with a charge of 0. So the substance that gets more negative is the hydrogen ion. Now, is there a spectator? Well, chloride starts as a minus 1 and it ends up as a minus 1. So the spectator that has no charge is the chloride minus 1 ion. All right, let's take a look now at the last example. Here we're going to have to go in and put in the charges. So let's go back and do that. Here we have an element all by itself. It's a 0 charge. Breaking it down, I see Ag2CO3. I recognize CO3 is a carbonate ion. It is a minus 2 charge that can be verified in reference table E. And each of these silvers is a plus 1. Okay. Over here on the product side, Al2CO33. Here's our CO3, which is a minus 2 charge. Each one of these aluminums, therefore, is a plus 3. And lastly, this silver product at the end is just going to have a charge of 0 because it is an element all by itself. So what substance gets more positive? What gets more negative? Well, let's track things. We've got aluminum 0 starting out as 0, but it ends up as a plus 3. So the fact is that Al0 gets more positive, means Al0 is what is oxidized. Now let's take a look at the silver plus 1. It starts out as a plus 1, ends up as a 0. That charge went down, so that means Ag plus 1 was reduced. And of course, you can probably see here that the carbonate ion, CO3 minus 2, is a spectator. There's no change in the charge. Okay. Now, let's take a look here. One of the things that you can do with all these skills is you can use these skills to help you predict products of a reaction. So in this case, I've given you mostly just reactants, and I'll ask you to complete or predict the products and then balance the reaction. So putting it all together, the first thing you have to do is you have to predict the reaction type based on the given products or reactants. You will then rearrange the elements using the reaction type as your guide. You'll then write proper formulas for compounds, remembering your diatomic elements, and then last but not least, you will balance the equation. All right, so let's take a look here. Example number 1, we have an element and an element. When you see two elements to begin with, the only thing that you're going to see happening here is synthesis. So that means we need to predict the formula of the compound that is formed from these two elements. So in order to do that, I'm going to do a little scratch work off the side. I need to know that silver is a plus 1 charge, and I need to know that oxygen has a minus 2 charge. So when I figure out the formula for that compound, it's going to be Ag2, 0. Okay. All right, what's left to do now is to balance the equation. I see here that there are 2 oxygens on the left side, but there's only 1 on the product side, so I'm going to have to put a 2 in front of the silver oxide to give me the oxygens I need, 2 and 2. That's going to give me 4 silvers. So I'm going to have to put a 4 in front of the Ag. So this equation balances as 412. All right, let's take a look at example number 2. Here I have potassium reacting with aluminum sulfate. I can predict what the products are going to be because I have an element and a compound. And in this case, the element is a metal. So this metal, K, is going to trade places with this aluminum. But when it does so, we have to make that formula correct based on the potassium ion. So I'm going to start by writing down what ions. K is going to form a K plus 1 ion. And this SO4 is sulfate, SO4 minus 2. So when I bring together potassium ions and sulfate ions, that chemical formula is going to be K2SO4. So this K is going to kick out the aluminum. It's going to form a compound, K2SO4. And that aluminum that just got kicked out is going to be its own element. Okay, now balancing this equation, I see that there are 3 sulfates on the left side. So I'm going to put a 3 in front of the K2SO4 to give me those 3 sulfates. That's going to give me 6 potassiums. That's going to give me 6 potassiums. So I am going to need to put a 6 in front of the K. I see that there are 2 aluminums here on the left side. I'm going to have to put a 2 in front of the aluminum metal over here. And I believe this equation is now balanced. Example number 3. We have FeO, and that's it. This is classic format for a decomposition. So we are going to separate this into its elements, Fe and O2. Remember, when oxygen is an element, not in a compound, it has to be diatomic. Iron is not diatomic, so we can just write Fe. Balancing this equation, I think I see that there's 2 oxygens on the right, but only 1 on the left, so I'm going to have to put a 2 in front of the FeO. That's going to cause me to have to put a 2 in front of the iron, and then I just need that one oxygen. All right, example number 3. I have sodium and MgNO32. This is going to be a single replacement. This metal is going to replace the magnesium. But remember, we have to make sure that we write the formula correctly. When I put sodium together with nitrate, I'm going to have sodium plus 1 ions and nitrate NO3 minus 1 ions. So this formula is for sodium nitrate is going to be NaNO3. That's going to cause the magnesium to just be out on its own as Mg. Now balancing this equation, I see that nitrates are out of whack. There's 2 here. I need to make sure that there's 2 on the side by putting this coefficient here. That's going to cause me to have 2 sodiums. I'm just going to fix that by putting a 2 in front of the Na. And everything else is A1. Okay. Let's take a look at the following examples. Okay, we've got a couple more examples to take a look at. Example number 5. Here we have a single replacement, but this time we have a nonmetal. So the nonmetal is going to replace the nonmetal over here. Okay. So what we are going to have here is we're going to have Ca reacting with Cl minus 1. So I'm going to have a CaCl2 plus I'm going to have iodine all by itself. Okay. And I believe that this chemical reaction is self-balancing. Everything just maintains a 1. It's so lovely when that happens. Equation number 6, this is a decomposition. NH3 is going to break apart into nitrogen and hydrogen, both of which are diatomic. So this clearly needs balancing. I have 3 hydrogens on the left, 2 on the right. I'm going to need to make sure I balance the hydrogens by putting a 2 here and a 3 here. That's going to give me 6 hydrogens on both sides. And that automatically is going to give me 2 nitrogens, and so this equation is balanced. Reaction number 7. I have 2 elements coming together. This is synthesis. I need to make a chemical formula with Mg and N. Magnesium's a +2, nitride's a -3, so this becomes Mg3N2 as the only product. Balancing this equation, I'm going to need to put, let's see, a 3 in front of the magnesium. Everything else here is a 1. Okay. Now these last 2 are combustion reactions. Combustion reactions always start with a hydrocarbon and oxygen, and they always end up with carbon dioxide and water. So we don't have to do too much fussing with figuring out what the chemical formulas are. We always know we're going to have CO2 and water. So this just comes down to finishing the balancing. For example number 8, I've got 1 carbon, 4 hydrogens, 2 hydrogens, so I have to double the H2O. That's going to give me the 4 hydrogens I need. And lastly, what's that going to do to my oxygens? I've got 2 and 2, so 4 oxygens here. I'm going to need to put a 2 in front of the O2. And that equation is now balanced. Last equation here, we have C2H6O, and this one is going to, CO3, that's supposed to be CO2. We've got 2 carbons, so we got to put a 2 carbon right there. We've got 6 hydrogens, we're going to have to put a 3 here. That's going to give me 6 hydrogens. And if we take a look, that's going to give me 4 oxygens plus 3 oxygens, so 7 oxygens over here. This oxygen is 1. I just need 6 oxygens out of this, so I've got to put a 3 there. So this equation is balanced at 1, 3, 2, 3. All right, so in this video lesson, we have learned how to predict products of redox reactions by recognizing the reaction types and then following our rules for writing formulas. Right? We have learned how to identify what substance gets oxidized, what substance gets reduced, and we have studied a little bit further synthesis, decomposition, and single replacement reactions. That's it for this redox lesson. I'll see you back in the classroom.